Hello, my name is Rose Connolly, and today I'm presenting perceptually guided, adjusted teleporting perceptual thresholds for teleport displacements in virtual environments. Our motivation revolves around a common locomotion method, teleportation. Teleportation solves practical problems given that it requires little space and compared to walking, low physical effort. However, as users are not visually traversing the space, it has distance and space effects. It can cause spatial disorientation and impair distance estimation. Of interest to us is that this can in turn lead to impaired personal space regulation. Existing work has highlighted that when users approach each other, they can teleport too close for their comfort and not really teleport due to the effort involved. And in this context, teleportation has been linked to personal space invasion anxiety. And so the use of teleportation with social interactions can be problematic. There are existing approaches that look at this problem. However, most are explicit and require effort. So there's negotiated teleportation, which reduces personal space invasion effectively. However, it does involve a sort of user interface in which the person teleporting, as well as the person being teleported to, can choose where the final teleport ends up. Social VR platforms such as Rec Room have personal space settings where you can choose the size of your personal space and customize who or what can enter the space. However, research shows these settings are often disabled by default and they're inaccessible, especially for novice users. And so they are inconsistently adopted. So we are interested in investigating an imperceivable form of adaptive teleportation to promote personal space regulation with little effort from the user. And so we explored redirected walking research to subtly redirect teleportation endpoints. Such methods are dependent on the perceptual limits of the user, which is the degree of change that we can tolerate without noticing. Such methods exploit our limitations and our abilities to sense changes in position, orientation, and even movement. And as teleportation is already a spatially confusing method, we wondered whether we could repurpose this to our advantage. Thus, we define perceptually guided adjusted teleportation as a redirected locomotion method in which the user's specified destination is altered in some way. In this study, our primary goal was to establish baseline perceptual limits for this method, so the degree of change that we could make to the teleport destination. We chose to focus these perceptual limits on small teleport ranges of about 2.5 meters and a large range of about 9. We also limited ourselves to forwards and backwards adjustments for the context of this study. We had a number of hypotheses also guiding our work. We expected that larger thresholds would be observed for backwards adjustments compared to forwards adjustments. This was partially due to the virtual environment that we use. We thought forwards adjustments would be more jarring and the expected view frame would more drastically change with forwards compared to backwards adjustments. We expected a larger threshold for large teleport ranges compared to small, and that's because large teleports have shown to have decreased pointing accuracy and distance estimation ability is impaired for larger distances as well. We expected that more experienced users in terms of VR experience would have smaller thresholds because this is true in redirected walking research. And we also predicted that users with better spatial abilities would have smaller thresholds, as this has been observed in other teleportation tasks. And so 30 participants underwent our experiment, which had 2 blocks for small and large teleports, and they were counterbalanced. In each block's users underwent a series of teleports. These teleports were either adjusted forwards, backwards, and then we also had teleports of no adjustment to serve as catch trials. For each condition, we had a staircase method to determine the perceptual threshold, which we'll see in the next slide. So we chose to establish perceptual thresholds with a psychophysical method called the staircase method. We chose this method because it's been used in redirected walking research already and is efficient, concentrating trials around the participants' thresholds. It adapts the stimulus strength. In this case, the stimulus is the distance that the teleport destination is adjusted, depending on the user response. As we can see here, the user was presented with a teleport and afterwards they were asked, do you feel you landed in the spot you selected? The stimulus or the adjustment value was adapted given their response. And there's more detail of this in the paper. We had 2 measures of spatial ability. We had a task, the spatial orientation task, which looks at your ability to take on different perspectives. And we had the Santa Barbara sense of direction questionnaire. The virtual environment was a square room, and the user would have to teleport to one of these 4. The virtual environment was a square room, and the user would have to teleport to one of these 4 destinations. The blue oval shows where they could possibly end up following an adjustment. And we had some piloting cues, so we had objects and paintings along the walls. And these are just visible for illustrative purposes, so this wouldn't be visible to the user. We see here an example of the small teleport range in which there's no adjustment. We see here an example of a forward adjustment of 2.5 meters. And this red dot shows where the adjusted teleport will end up. Again, this wouldn't be visible to the user, it's just for illustrative purposes. Here we have the large teleport condition. So this teleport has no adjustment. This is a forward adjustment and a backwards adjustment. And so our results. So this graph shows the average perceptual threshold for our participants for each condition. As we can see, our largest threshold was 1.64 meters for backwards adjustments across large teleport ranges. Our smallest perceptual threshold was for forward adjustments across a small teleport range, although still quite large at 0.75 meters. So we tested if these conditions were significantly different, and as per our first hypothesis, there was a significant difference between backwards adjustments. They were larger than forwards adjustments. As per our second hypothesis, perceptual thresholds were significantly larger for large teleport ranges compared to small, and there was no interaction across these conditions. So we had expected for more experienced users to have smaller thresholds. This was true, but only for backwards adjustments across small ranges. Expected users with higher special abilities to have smaller thresholds. And this was also partially true. It was only significant for large backwards adjustments. And we did have non-significant correlations for some other ones. We had expected users with higher spatial abilities to have smaller thresholds. This was true, but only significant for large backward adjustments and only for the spatial orientation test and not the Santa Barbara sense of direction questionnaire. And thus H3 and H4 we could only partially accept. So backwards adjustments were less detectable overall. And that's probably due to the virtual environment. They were teleporting towards this corner, so forward adjustments would kind of cut their expected field of view more drastically than a backwards adjustment. The perceptual threshold increases with teleport range. So that's as we expected, probably due to decreased pointing accuracy and distance estimation abilities for a larger range. Forward adjustments had universally detectable because there's no correlation with participants' VR experience or spatial ability, unlike backwards adjustments. We only saw correlation with the spatial orientation test of spatial ability. So this might be a more reliable indicator of ability to detect adjustments compared to the Santa Barbara sense of direction questionnaire. This could be because it's objective as a task, or it could be that it targets mechanisms more suitable for detecting adjustments. We also asked users what type of strategy they were using to make their decision. Participants mentioned using walls and paintings as landmarks. Some mentioned that they would try to imagine what their viewpoint would look like following a teleport. There's also some aspects of triangulation, so trying to figure out where you are or where you would be in relation to other objects. And so we see our main application of this method to correct overshooting in social VR. This would be quite relevant, seeing as we saw that backwards adjustments were quite undetectable. As such, it could be used to prevent personal spies. We see applications of this method in correcting overshooting in social VR. This may be particularly feasible given that backwards adjustments were generally undetectable, and as such, this method could be used to prevent personal space violations. It can also be used to subtly guide players towards objectives or goals. It could be an adaptive locomotion, especially for novice users, and such adjustments could be lessened as users gain in experience or skill. Our experiment is, of course, limited to the virtual environment that we used. It would be interesting to replicate this in an open world environment. We didn't test the application of this method, so we're currently working on that. Users were, of course, focused on the task itself, which was detecting adjustments. If they weren't, we might find that, like in redirected walking research, perceptual thresholds increase when users are not focused on detecting. We only explored forward and backwards adjustments, so we could explore other directions as well as rotations to teleport destinations. Future work could also consider user feedback loops. So if a user is adjusted, we could also consider user feedback loops. So if a user is adjusted, but re-teleports to their original destination, perhaps next time you would lessen the adjustment. However, of course, you'd have to carefully consider user data privacy. And so in the study, we found that teleport destinations can be adjusted without being noticed. This adjustment magnitude was quite large. There was large perceptual thresholds we see for backwards adjustments, up to 1.6 meters of adjustment. Larger teleports seem to allow larger adjustments. Individual spatial ability and experience with VR may play a role, especially for backwards teleports. However, forwards adjustments seem to be more detectable overall. Thank you.